There are some pretty big mysteries in astronomy. What is dark matter? What is dark energy? Why was there more matter than antimatter in the early universe? What's inside the event horizon of a black hole? These are complicated mysteries, and we may never know the answer. But there are other mysteries that feel like we are making serious progress, and one of these is the mystery of fast radio bursts. These came out of nowhere back in 2007. Astronomers detected this bright flash of radiation that seemed to be coming from halfway across the universe, and yet only in this very specific wavelength of radio waves, and they don't seem to repeat. They happen randomly in the sky. What is their cause? We don't know what they are, but they appear to have something to do with magnetars. These are a type of neutron star that have intense magnetic fields that can lash out, and it's believed they can release flashes of radiation. Or maybe it's neutron stars colliding. We still don't really know. My guest today is Dr. Fengqiu Adam Dong. He is a Jansky Fellow for the National Radio Astronomy Observatory, and he works at the Green Bank Observatory, which is funded by the NSF. And he is currently at a conference in Montreal discussing fast radio bursts, and also had a really interesting new discovery that he was announcing at the conference. And so I had a chance to talk with him while he was in between sessions and was able to give us an update both on what is the current knowledge about fast radio bursts, and then his specific research, which is about a really interesting long period radio transit, which is something that is behaving like a pulsar long after it should have been dead. We talk about that as well as just other aspects of radio astronomy and pulsars in general. So if you're interested in fast radio bursts, I think you'll enjoy this interview with Adam Dong. Adam, this is kind of cool. You're in Montreal right now at an annual conference just to talk about fast radio bursts. And when you think about the history of this, like, we've only known about fast radio bursts since what, 2007? And now there's so much research going on that there's like people are coming from around the world to just talk about fast radio bursts.
Yeah, it was very cool. Actually, when I was flying in to the conference, there's a parallel conference called ExoCLIME, so exoplanetary climates, going on in Université de Montréal. So, there was I flew with a whole bunch of exoplanet astronomers as well. So I managed to, get the lowdown on TRAPPIST results and things like that. So, that was pretty cool. But, we had a whole bunch of astronomers at McGill talking about fast radio bursts. We had the discoverer of the fast radio burst there, Dunk Lorimer.
Oh, wow. That's amazing.
Yeah, that's great. Yeah, well, Dunk is at West Virginia University, so he's actually very close to me at Green Bank, and he comes and visits every once in a while. So, he was there. It was wonderful. Yeah.
I always use fast radio bursts as an example of a mystery that we are, for all of the mysteries, we kind of don't even know where to start. What is dark matter? What is dark energy? Fast radio bursts specifically seems like one of these mysteries that has been cornered, and you guys are zeroing in on what the underlying cause of this is. But before we get to what it almost is most likely to be, what are the characteristics of a fast radio burst?
So characteristics of fast radio bursts, well, it's really in the name, right? It's fast, which means it's milliseconds in time scale, or even shorter, as we found out at the conference. Sometimes they can be really short, microseconds even.
Wow.
They're only in radio. So to date, I believe we've only seen fast radio bursts in radio, which means that this is kind of strange. If this thing is so energetic, why would it be only in radio? Why would we not detect something in visible light or in high energy? And it's a burst. So, it goes boom, and then you don't. Sometimes you see it happen again, sometimes you don't. So that's what a fast radio burst is. Some repeat, some don't. They're very interesting objects.
And I remember it was even just a couple of years ago where astronomers finally said, okay, we're pretty sure these things are coming from outside the Milky Way, that there was a telescope, maybe it was CHIME, but there was a telescope that wasn't able to focus on anything that was relatively close. And so it was able to detect the fast radio bursts. And so they knew, okay, we know for sure that these are extra solar system in location and probably even extra galactic. Are we pretty sure how far away these things are coming from now?
Yeah, So let's unwrap that. So when the first one was discovered, we were already then pretty sure that it was extragalactic and coming from outside the galaxy, which instantly makes them super interesting because that makes them way brighter than anything we see that pulses like that within our galaxy. And then there was a period of time where the Parkes radio telescope in Australia found a whole bunch of, quote, fast radio bursts, and they named them peritons because they knew right away, basically, that they were probably fake or they were radio frequency interference, RFI. And they knew this because they were too bright in the detectors, and they found out that it was a microwave on site because they found more of these.
I remember that.
They found more of these at lunchtime. So, yeah, so that was a very fun history experience. So now we're really careful, right? So now we're being very careful about this, and we're systematically ruling out anything that can be terrestrial, so anything that can be generated from Earth or even things orbiting Earth, like satellites and things like that. So we're fairly sure most of these are from, I say most because there's one that could be from within the galaxy, but everything else is outside of the galaxy. And so they're all really bright.
Right. And like, how far away? Like, what do we think? Give me sort of a sense of scale. How far do we think the closer ones are coming from? And then how far away are the most distant ones coming from?
Yeah, so the closest ones, so one of the closest ones is coming from the M81 galaxy. That's about 3 megaparsecs away.
Right, about 10 million light years.
Yeah, if I remember my numbers correctly. So the conference, this is public information because it was shared at the conference, but I think ASCAP, or is it MEERKAT? These are two radio telescopes, one in Australia, one in South Africa. I can't remember which one it was, but they announced that they found a fast radio burst from redshift 2, which really puts that cosmological. I can't convert it into megaparsecs in my head. I'm sorry.
A redshift 2, that's 3.3 billion years after the Big Bang.
So it makes these really cosmological things. Fast radio bursts are now being used to probe the material between us and wherever it originated from. And so it makes them really interesting because we can probe the density of matter between us and the fast radio bursts because they're so far away, basically.
So then you've got this flash of radio waves that can be a fraction of a second, and yet the radio waves are able to travel that far. So how much energy is being produced to be able to generate that kind of radio emissions?
Oh, yeah. So it varies between fast radio bursts. Like, you can probably imagine the very far away ones have to produce more energy for us to detect them, as energy falls off as the square of the distance. So you have to produce a lot more energy the further away you are. The general sort of numbers or idea I like to put in people's heads is that you have to accumulate days to weeks of energy from the sun, and you got to compress that all down to a millisecond and flash that at our telescopes for us to be able to detect it, to get to us.
Yeah, but then you're getting that much energy and you're not seeing other wavelengths at the same time. So it's very specific, which has deepened the puzzle.
That's right. Yeah, it's very strange. So you can do this with, people have come up with theories. Pulsars are another type of object that sort of do this. As you said, fast radio bursts have been cornered into this regime where we pretty much know it's a neutron star. Well, what else is a neutron star? A pulsar is a neutron star. Pulsars are mostly seen in radio, hence the name radio pulsars. And often they're not seen in any other frequency as well, because of their emission mechanism, right? So sometimes they're seen in very high energies like X-ray. And I think one or two, like the Crab pulsar and the Crab nebula, is seen in optical and visual bands. But apart from that, pulsars are exclusively seen in radio, and that's why we only observe them in radio. And same with fast radio bursts. Yeah.
All right. So, and I think that sort of sets the stage then for what has got to be a very bizarre object, because you've got this compact object that is releasing weeks worth of stellar radiation in a fraction of a second, and it's only coming out in the radio waves, and we're not seeing it in these other wavelengths. So what is the most likely culprit? Or maybe, we can narrow down what are some of the culprits that people thought could have been responsible for fast radio bursts?
Yeah, you've hit the nail on the head there, right? Like, a lot of people want the answer to this question. It's difficult to answer because theorists have come up with different theories, but what we have seen, what I can't tell you is that as somebody who observes the sky, what we have seen is that there's a magnetar, which is a very high magnetic field pulsar, and that magnetar has burst, I think in 2020 or something like that, and it released a whole bunch of energy. We detected it with the CHIME telescope. The STARE-2 collaboration also detected it. And that is what is often called the first galactic fast radio burst. And why that's so valuable is that because we know exactly where that came from. And so we know the properties of that magnetar. We've been observing that magnetar for years in radio and X-rays and optical, etc. So it's very valuable information. So we know that at least a portion of them must be neutron stars. Now, can there be a portion of them which are, for example, binary neutron star mergers? And we just don't know the answer to this. And at the conference, actually, it was very funny. The organizers let us choose pins and like to clip on your lapel. And there were things that they said, all FRBs are repeaters. And there was a camp that said there are N populations, so there are N, like multiple types of FRBs. And then there was there are repeaters and there are non-repeaters. So there's two types of FRBs, and everybody chose a camp to fall under, and it was pretty evenly split. And we had joking fights between the camps and everything between scientists. It was pretty fun, yeah.
So about 50% of people believe that it's a one-time event, something like the collision of two neutron stars, while half of the astronomers there believe it's some kind of repeating thing, like a magnetar having some kind of twisted magnetic field and then releasing it and then doing it again, like a flare on the sun.
Yeah, so almost. So everybody knows that at least some FRBs must be magnetars, I think, because we've seen repeaters and we've seen this magnetar give off an FRB. So at least some FRBs must be magnetars. But what not everybody agree on is that all FRBs are magnetars. So some people think that a subpopulation are magnetars, and then another population are maybe binary neutron star mergers, or maybe some weird sort of supernova or something.
Yeah. And are black holes completely ruled out at this point?
You know what? I don't know the answer to that. There's a
It wasn't a pin though you could pick.
No, there was no pin. There was no pin that you could pick. So I don't know the answer of the black holes are totally ruled out. I'm sure there's a theory that espouses that you can have a black hole doing something weird, producing a fast radio.
Right.
But,
yeah, a magnetar going through the accretion disk of a black hole or something. So right, but then you're back to it being a magnetar. So I guess if I was to like conduct this random poll, and I love this, right? Because the fact that even the astronomers right now at the conference, like this is where you are right now, is at the conference to figure out what to talk about fast radio bursts, and you're going to get disagreements. We don't entirely know what they are, but they seem to have something to do with magnetars, colliding neutron stars, or they have something to do with neutron stars colliding or their magnetic fields. What will it take to figure out their true identity?
That's a great question. What would it take? Let's see. So one thing that really helps is to be able to localize. And what I mean by that is be able to pinpoint exactly where it is on the sky. We haven't been able to do that so far, especially with CHIME. And CHIME is this Canadian telescope, and it's discovering a whole bunch of these fast radio bursts. But we haven't been able to do that because CHIME has pretty bad localization capabilities today. But what we have done is we've built what we're calling outriggers. So they're little versions of CHIME, and we put one at Greenbank Observatory, we put one at Hat Creek, and we put one near the town of Princeton in British Columbia. So we have 3 extra little chimes that form a VLBI baseline, and the maximum baseline is 3,000 kilometers. And so now, if we see an FRB, we can, with CHIME, we can pinpoint it to about 50 milliarc seconds, 100 milliarc seconds, sorry. We can pinpoint it to 100 milliarc second precision on the sky. And what that allows us to do is where we can see exactly which galaxy it came from. And not only that, we can see where in that galaxy it came from. And so you can imagine a situation where, for example, you have an old dead galaxy that's not forming much stars. Well, if it's not forming much stars, it's probably not producing many big stars that are producing explosions to make neutron stars and magnetars, right? Magnetars are generally pretty rare. And so in that case, if we localize them all to all these dead galaxies, then you can say, well, they're probably not young magnetars. If they're magnetars, they must be old, right? So we're just at the stage of starting to collect the information of which galaxy these sparse radio bursts are coming from. So other telescopes like the Deep Synoptic Array, DSA 110, have localized a few. ASCAP has localized a few. In total, we've got about 100 or so localized to galaxies right now. With CHIME, we expect to do thousands. And so we hope that with CHIME, in the next year, 2 years, 3 years, we're going to be able to pinpoint a bunch of these FRBs on the sky to galaxies. I think it'll be a really exciting time to be in this field.
Right, I understand. So in other words, you know that you can kind of classify the galaxy, and then if you find they're popping up in a bunch of old galaxies, then that starts to shift the evidence away from them being magnetars, which require huge regions of active star formation. And I wonder if you can localize them down to that level, then maybe you could do follow-on observations even in other wavelengths, like say with James Webb or with Hubble, to say, did this come out of a star forming region or did this not? Did this come out of the arms or did this come out of the halo?
That's exactly what we're doing. Yeah, right on the head again. Yeah, so we're already starting to localize. All of our outriggers are online. And we have a special team within CHIME, and they are very good at writing proposals to other telescopes and to optical follow-up campaigns. They have triggered proposals already accepted. We recently got a JW proposal accepted and also observations made. And so, all of these things combined means that as soon as an FRB happens, that's interesting, we localize that right away. And then we already have a triggered proposal accepted. So we just tell, for example, the Gemini telescope, okay, go point that way quickly so that we can see if there's anything going on there and things like that. At the very worst, we can get the redshift of the galaxy that the FRB came from.
And it would be amazing to also, maybe if a gravitational wave telescope can detect something at the same time, then you could go that other route and go, okay, no, this is possibly due to colliding neutron stars. So either way, that's really interesting.
It's too bad LIGO's banana curves are huge. So it's too bad that they don't have our localization ability.
Right. I mean, with Kagra and Virgo joining the hunt, you get more sort of I guess nuance in finding out where these things are coming from, but we really are going to need those next generation gravitational wave detectors to come online before we can get that level of specificity. Yeah. Well, I want to shift gears because we're talking not because of fast radio bursts, although I'm kind of obsessed with them. And so I wanted to lead with that. But you've actually got a new piece of research that's just dropped today. Now, were you announcing this at the conference as well?
Yeah.
So what did you find?
Yeah, it's really cool. So in the past, and you mentioned in 2007, fast radio bursts were discovered. Is that right? Yeah, okay. So
Yeah,
in
I think so.
2007, pretty recently, fast radio bursts were discovered. But, a few years ago, Natasha Hurley-Walker from Curtin University in Australia, she discovered these things called long period transients. And so what they are is they're like a pulsar, but the periods are so long. The periods in hours are of order hours, or at least tens of minutes. And so you can start being like, well, hold on a second. Are they even possible under the pulsar regime? They look like pulsars. They pulse like pulsars. But all our theories for pulsars, how they burst, how they pulse, the energetics that required, some of them seem to break down for these long period transients. And so that's why they're so weird. And we never expected to find them. And so, Natasha, Dr. Hurley-Walker found the first one. And then everybody else started looking, right? So we found some in our data. And so this is a growing field. And we found a very, very interesting source. It pulses on an 841-second period, which is about 14 minutes. But there's also a secondary period going on. We're not sure what the secondary period is, but there is a secondary period. It's about 5 times 841 seconds. In fact, exactly 5 times that.
I mean, when we talk about pulsars, we don't talk about them taking 841 seconds. We talk about them happening 841 times a minute, right? Like hundreds of times a minute, not, minutes long for each one to happen. And so, but does it, if, a pulsar, you're seeing these flashes hundreds of times a minute, does this look exactly the same, but it's just taking this extremely long period of time? Or does it have any different characteristics to it?
Yeah, that's a great question. So for our ones, they actually look very similar to pulsars. They produce bursts that are commensurate with the period. So, you imagine a pulsar that's 1 second in period produces a 10 millisecond burst. Our 841-second period pulse object, long period transient, produces a 4-second burst. So it's kind of like commensurate in ratio of burst length to period length. And the burst structure is, if you have seen the photos, they look very spiky. So maybe not like a standard pulsar, but they often look like magnetar bursts. The magnetar bursts do this where they look super duper spiky. And so there's been lots of speculation like, oh, is this a magnetar? Like, is this a really, really old magnetar? Maybe it is.
Well, and I understand that pulsars, like, they die. I mean, they don't die. That when a star goes supernova, all of that angular momentum is still maintained, and you get the pulsar, and the pulsar is spinning rapidly and interacting with its environment. It's got this magnetic field, and it's blasting out waves of radiation, but it is also slowing down over time. And eventually those radio waves will shut off. At what point will a pulsar typically stop emitting those waves of radiation?
Yeah. So how radiation for pulsars are thought to work is that you have this strong magnetic field, the pulsar spinning really fast, and then you have electrons that are, or charged particles that are dragged along the magnetic field lines, and those particles emit radio emission. So there's a diagram that us pulsar astronomers like to use. It's called the period spin down diagram, and you can draw a line through it and say, okay, anything below here, you cannot spin the charged particles quick enough. Oh, sorry, you can't accelerate those charged particles quick enough. so that you can generate the emission. And that's when they, quote unquote, die. And so pulsars will spin down, they will lose energy as they emit radio emission, they will spin down and they'll get slower and slower, and then they'll die, usually, is how we think of it. Yeah.
But it's well before 841 seconds, isn't it?
Oh, yeah. It should never reach that long. It sort of just, it will just die, at a few seconds, probably. It should never reach, 800 and something seconds. So it really is quite weird that we're finding pulsar-like emission at that high period.
And so what do you think is the underlying mechanism? How can you get something that is behaving like a pulsar and yet it should have died a long time ago?
Yeah, so I mean, there's a lot of theories. I don't know how many of them are sticking right now.
I guess, are they handing pins out? Do you think?
Yeah, I mean, there's about two camps, right? There's actually two camps of people in this very new field that's only a few years old, and these are white dwarfs, or these are neutron stars that are spinning really slowly. Personally, I think that both are correct. So there are some that are clearly neutron stars and some clearly white dwarfs. And so with the white dwarfs, you can have some pretty interesting dynamics going on. For example, they can be in a binary system. If they're in a binary system, you can maybe, it's called like a magnetic bridge. You can like form this bridge between it and its companion. You accelerate charged particles along this bridge, and that's where you emit this burst of light. Instead of the poles of the object of the pulsar accelerating the charged particles, you accelerate along this bridge. Or you could have its companion throw some mass, throw some plasma or whatever onto the white dwarf, or the other way around. The white dwarf throws some mass onto its companion, most likely an M dwarf star, and that can create a pulse of coherent radio emission. Yeah, so there are a few theories. For a neutron star model, usually it's this like old magnetar model. So what you have is you get a magnetar that's born maybe period, I don't know, 3 seconds or something like that. And then it slowly spins down really quickly because of, kicks that it does, because the magnetar does weird things, and it kicks itself down into this long period regime. And then it's not getting energy. The energy that it's getting isn't from the spinning of the magnetar anymore. It's not what we call rotationally powered. It's getting its energy from its very dense magnetic field. And so these pulses that you see, it's just drawing energy from its magnetic field, and it's releasing it, like it's pulsing that out.
Right, like a capacitor almost.
So something like that. Yeah.
Right. Oh, it's interesting. And so with the binary object, you're sort of imagining maybe something's on an elliptical orbit, like a really highly elliptical orbit, and then it's coming close and sort of passing through some region that's kind of releasing the particles, and then it's moving away again. Is that sort of the idea?
It's constantly accreting material from
right, or it's just getting constant material, and then it builds up to almost like the way a white dwarf can move towards becoming a nova, but with like a very quick nova that only shines in the radio. It's a very weird puzzle. But what was special about the object that you guys are working on?
Yeah, so one thing that's really cool about this thing is that so I mentioned that there's this double period for some reason. We're pretty sure the period is 841 seconds, but there is this secondary period. We're not really sure what that secondary period is. We think it's to do with a binary, secondary object in the system. So that's something that's, kind of still a mystery that I hope somebody will solve. We put the paper out there. We hope other astronomers will come and help us solve it. The other really cool thing is that it's spinning up. And what I mean by that is that its period is getting slightly faster over time. And we've been monitoring this over, 8 years, so about 4 years. And the period is getting slightly faster. And so what that means is that it must be getting energy somehow. If it's just a solar object, and the period is from its spin, so it's spinning, and that's the period that you're seeing. It must be getting energy somehow to spin faster, because we don't really like when energy is not conserved. But I mean, a very out there speculation that we have in the paper is that some long period transients, we've seen its radio period, and we know that some are in binaries. So we see its orbital period; they're locked. So the pulses you see are locked to its orbital period. And if it's spinning up, that means the orbital period is decreasing. And so what that means is the actual orbit is decreasing, the orbit's getting closer and closer together. And we've seen something like this happen before. We've seen this in pulsars, we've seen this in white dwarfs. And this happens because it can give off gravity. The orbit, the binding energy of the orbit can be given off as gravitational waves. And Einstein predicted this. This will happen. So maybe this is why it's spinning up. But really, it's really difficult to say right now why it's spinning up. We know is that it is.
So just to understand, because these things are orbiting around each other in a kind of a lopsided way, that's bleeding off gravitational waves as they move around each other. Moving mass creates gravitational waves. And then is that like bringing them closer to each other and then causing this spin up?
Yeah, that's right. So,
right.
So if the orbit, if the period we're detecting, this 841 seconds, is not a spin of the object itself, but it's the orbit that we're detecting, because that has been the case for some of these long period transients. Then, if the orbit is decreasing, it has to give off that energy, what we call the binding energy of the orbit, as gravitational waves. So it's kind of similar to when you see LIGO get mergers, right? That's the very end stage of this spiraling process, and they give off this huge chirp, and then you see it. But we may be seeing, and I'm not saying this is the case. This is just a speculation that we say in our paper, is that you see this orbit getting smaller, and then the reason for that is gravitational wave emission.
Oh, that's really cool. But Adam, what are you obsessed with right now?
Yeah, so a lot of my research is on pulsars. So I'm obsessed with pulsar surveys, timing new pulsars. CHIME is now part of the Nanograv observatory set of observatories. So I'm obsessed with basically everything to do with pulsars, and now these new long period transients as well. So finding new cool things in the
Nanograv
sky,
experiment. The Nanograv experiment, that's using pulsars to detect the background gravitational waves of colliding black holes. Pulsars feel like this really wonderful tool that, because they're essentially just space clocks, you can then use them for all kinds of things. So what are some like really creative ideas that people have suggested for using that you could use pulsars for?
There's tons, right? Like, instead of a GPS, you can have a universe PS, the universe positioning system, right? Anywhere you go in the universe, and you look at a few pulsars, you know exactly where you are, because pulsars are very easy to identify which one they are, because they have a very, very precise period. And so you can just, exactly pinpoint where you are. That's, one of the far out ideas. But I recently read a paper where they said, well, all of these globular clusters are clusters where there's a lot of stars and gravitationally bound and things like that. They might have a intermediate mass binary black hole inside of them. And
I saw that paper.
Yeah, conveniently, there's all these pulsars that are surrounding it. Well, let's use the pulsars. Let's try to detect the intermediate mass black hole binaries in the globular clusters. Can we do that? Maybe.
So you could detect, as this black hole is moving through the cluster, it's sort of pulling gravitationally against these various pulsars back and forth as it moves like a wake, and you would detect their movement and try to trace the movement of this black hole through the cluster.
So that's one way of doing it, if it's just one black hole. But if it was a binary system, then it should be giving up gravitational waves. So just like the regular pulsar timing array, where you're detecting gravitational waves from supermassive black hole binaries, in this system where the pulsars are so close to the intermediate mass black hole binary. Actually, the pulsars or the pulsar's position should be shifted just slightly. They should be wobbled because of the gravitational waves emitted by the intermediate mass black hole binary in the middle of the globular cluster. And then the wobbling will cause us on Earth to go, what's going on there with these pulsars? And that might be a signal of something interesting going on in the center.
Oh, that's really cool. Yeah. So if you have pulsars that are nearby things that are emitting gravitational waves, maybe that's a way to zero in on them as opposed to having to try and detect them just generally across billions of light years. You can actually see pulsars nearby something reacting to those gravitational waves.
That's right. Really interesting. They're amazing clocks. Yeah.
They're like atomic clocks, natural atomic clocks out there in the universe that we can just use if we can think of clever ideas to use them.
Exactly.
Well, Adam, thank you so much for taking the time to chat with me today. Good luck with the conference and with your research, and I really appreciate it.
Thank you. Yeah, that's great being here.
I hope you enjoyed that interview with Adam Dong. Now, I had a longer conversation with him about the CHIME telescope. It's in my province. I'm kind of fascinated by this telescope. And so I wanted to know a little bit more about how it works. And so we have a longer conversation over on Patreon where Adam talks about his experience with the telescope, how it works, why it's such a effective fast radio burst hunter. Now, I'm going to put a link in the show notes over to that version of this exact same interview, but with the additional content. That's interview plus. So go and definitely check that out over on Patreon. All right, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bray Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nelson, David Gilton, David Matz, Dustin Cable, Evan Pro, Greg Feely, Hudson Moore, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Marcel Smith, Michael Purcell, Monzo, Paul Roebuck, Ren Kaidu, Robeck, Sean Sargent, Stephen Fowler Munley, Vlad Chiplin, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So in addition to fast radio bursts, I am also quite interested in pulsars, and there's a lot of really interesting interviews that I've done related to pulsars, both how they can be used, this idea of the nanograv experiment, that you can use pulsars as gravitational wave detectors to be able to sense the background gravitational waves of colliding supermassive black holes. And then also, can you get a pulsar? What happens if a pulsar is feeding on material with some kind of companion star? These are known as black widow pulsars. And it's sort of right there in the name that you've got this pulsar that is feeding on material from some binary object that can cause it to behave a little more strangely. So I'm going to put some links to some other interviews down in the show notes if you want more information. All right. I hope you enjoyed the interview, and I will see you next time.